This has to be magic! Hi, I'm Uri, the creator of Wokwi and also the co-founder of Tiny Tapeout. So what's Wokwi? It's the world's most advanced ESP32 simulator. It works in VS Code, in JetBrains, in your browser, and even in your CI/CD pipeline. We are going to see some real-life examples of using Wokwi, learn how to set it up for your projects, and explore some of the more advanced features such as Wi-Fi simulation, CI/CD scenarios, and custom chips. Let's dive in. Go to wokwi.com, click on ESP32. We have a big bunch of examples here, or we can start from scratch. You can see we have the ESP32 family of dev kits and some third-party boards like the S3 box or M5 stack. And we can write code in Arduino, MicroPython, or even use ESP32 code if you are feeling adventurous. Now, let's see some example. I like this one, the joke machine. I click on it. On the left, we see the source code. This is Arduino code. And on the right, we see the diagram with all the connections. And all we need to do, just press play to start the simulation. And now it's connecting to the virtual Wi-Fi. It will get an IP address in a moment, connect to the joke HTTP API server. And no, I'm not going to read this one out loud. Now let's go back and see another example. This time it's a MicroPython example. And this is going to connect to an MQTT broker and report the temperature from this DHT22 sensor. So first of all, before running it, let's open this web-based MQTT client, put them side by side, adjust the size of the window. And let's get this MQTT client connected to the same MQTT broker as this MicroPython code is going to connect to. So we are connected. And now let's subscribe for this topic. It says here in the instructions, Wokwi weather. You can see that the code also uses the same topic name to publish the MQTT messages. So I'm going to add a subscription, subscribe, and start a simulation. And now the MicroPython code is running and it's going to connect to the Wi-Fi. It's connected to the MQTT server and we can see the message. And if I click on the sensor, I can change the temperature and you can see the messages coming from MicroPython right into the MQTT broker. And if I want to go back to MicroPython, I can just click Ctrl+C and start interacting with the REPL. Like, let's see what we have in this sensor object. We can see we have all these members like sensor.pin that tells us which pins the sensor is connected to. And we can take another measurement and print sensor.temperature or just greet hello ESP DevCon. Yeah. So far we have seen two client examples, an HTTP API client and an MQTT client. The next one is actually going to be an HTTP server running on the simulated ESP32 and controlling two LEDs. Let's read the instructions. So first of all, we need the Wokwi IoT gateway. It's a small app that allows the computer or the browser to connect into the simulation, into the HTTP server. And you can see all the instructions here. It's a paid feature. And I'm already running it on my machine. So we can just go back and press play to start the simulation. And it tells us we need to open this link. Let's go back into side-by-side view, open the link, and voila! This is the web page that you can see here, the source code for this web page served from the ESP32. And we can click to turn on and off each of the LEDs. And if we scroll down a bit, we can actually find here this code that handles the toggling of the LEDs. It listens on the /toggle URL, and then depending on the LED the index of the LED that it gets from the path, like this is LED number 2, it just toggles the state of the LED. If we refresh the page, we can see it actually toggles it on each refresh. Now, do you see this little Wi-Fi icon here? It shows you the connection status, but when you click on it, you can uncover one of the more powerful features of the simulation. downloading the Wi-Fi packet capture, aka pickup file. When we click on it, we get a file that we can open in Wireshark, and then we can see all the Wi-Fi traffic that went through the virtual access point during the simulation. We can see the Wi-Fi beacon advertisement, so Wokwi guest is the name of the virtual access point that we have in the simulation, and if we go down we can see the Wi-Fi association and then the DHCP negotiation where the ESP32 gets its IP address, and further down we can see the HTTP request and the responses, and if we right click and follow HTTP stream we can see the request that my Chrome browser sent and the response that we got from the ESP32 HTTP server. This feature comes really handy when you need to debug connectivity or protocol level issues. Okay, let's go back to the browser. One thing I want to show you, when you click on the ESP32, there is this question mark. It takes you right to the documentation. And if you scroll down, you can go to simulation features and you can see all the simulated ESP chips and which features and peripherals we simulate. So PSRAM, UART, USB, some are not yet supported, but we are working on them. And speaking of documentation, if you ever forget how to connect to the virtual Wi-Fi, just go to the ESP32 Wi-Fi guide, where you have the name of the virtual access point, the channel, and you can also see the IP address and the MAC address of the simulated ESP32. Up to this point, we have seen 3 IoT simulation examples, and they all run in the browser. Now, this is great if you want to quickly prototype something or you want to share your project with friends or colleagues. And it's also great for classrooms and workshops and other educational use cases. But what if you want to work locally and use your favorite development tools like Git and your favorite IDE? Enter Wokwi for VS Code. Let's start with a quick example. This is a project using LVGL ESP-IDF project, and it just displays, scrolls some text on an OLED display. Now it's already set up for Wokwi, so if we click on diagram.json, we can see the ESP32C3, the connections, and the OLED display. And all we have to do is just click play to start the simulation. And we can see this terminal window with all the output from the boot ROM and the log messages from the application. And then on top, we can see this text scrolling. Now, let's say we want to make a change to this code, so we can open the code side by side with the simulator. Let's put the code on the left, the simulator on the right, and then let's change this text to say, hello, Espressive DevCon24, and save, recompile the code, and it's now, no, not flashy, just recompile it. And now it's rebuilding the code. It will take a few moments to recompile this code, and Wokwi actually monitors the binary, and voila, it found that we updated the binary and we get immediately to see the new code running. No need to wait for flashing. Our friends at Espressive even coined a term for this, Wokwi style of development. So even when they develop on the physical device, they still use Wokwi to test their changes while they are waiting for the firmware to flash. All right, let's explore the debugger now. I'm going to set a breakpoint here in the loop, press F1 and start Wokwi in debug mode. And this starts the simulation. And now I need to press F5. Let's put the simulator side by side with the code first. We need to keep it visible while we are debugging. And now I'm going to set F5. This will tell VS Code to start the debugging session. It takes a few seconds and we can see the debugging session has started. And we hit a breakpoint. Yay! Now, do you see these labels next to the pins? We call this feature pinned up, and it appears whenever you pause the simulation, even without using the debugger. This is very useful to spot connection errors or misconfigured pins. And for instance, we can see here that pin 3 is set to I2C0 SDA. It actually is connected to the SDA of the OLED. Pin 4 is set to SCL, and pins 5 through 7 are configured for JTAG debugging. Well, back to the breakpoint. We can step through the loop and see the display updating as we go. We can see the counter going up as we step through the loop. We can also inspect the variables. For instance, this label, this uptime label, we can see it here. We can take a look at the coordinates X, Y, and we can even cheat the uptime here on the right side and bump it up, let's say, to 1000, and then continue the simulation to see it updating here, 1001. On the right side panel, we can also see the call stack. And if we want to dig deeper, we can even take a look at the CPU registers, or go to this memory dump and see the contents of the ESP32 memory. And there is my favorite, this peripheral viewer lets you take a look at the peripheral registers, like for instance, the I2C, where are you? I2C registers. You can read all of the registers, the interrupt status, and I like this one, the RNG, because every time it returns new random generated value. One of the best things about debugging with Wokwi is the number of breakpoints that you can have. On the real ESP32, you can have up to 2 hardware breakpoints and 2 hardware watch points. And with Wokwi, there is no limit. You can have as many as you want. Yeah, that's right, as many as you want. Now, let's see how you can add Wokwi simulation to an existing project. We'll take the Hello World example from ESP-IDF and see how to quickly set up for simulation. First, we are going to install the Wokwi command line tool that is going to help us set up the project. There is a command for Linux, and I will copy the second one for Windows PowerShell. Go to my command line, paste the command, and bam! I got a CLI, it's installed. Let's go to VS Code. This is the Hello World example from the IDF, and I already built it with idf.py. Now, all I need to do is just, let's clear the screen, type Wokwi CLI init, and it runs. It detects that this is an ESP-IDF project, so all I need to do is to select the board. In this case, I built it for the C3, so I will choose the C3 dev kit. Go ahead with the default firmware and ELF file location, and that's it, ready to simulate. The CLI did 2 things. It created this diagram JSON file with the dev kit, the C3 dev kit as we told it, and also this wokwi.toml configuration file. This file tells Wokwi where to find your firmware, and check this link for more options like TCP port forwarding, which is useful for the ESP32 web server that we saw before. Let's see another ESP-IDF example. This one is generic GPIO. It configures 4 GPIO pins, 2 as outputs and 2 as inputs with interrupts. And we will be using the C3, so these are the pin assignments. Outputs are 18 and 19s, and the inputs are GPIOs 4 and 5. I've already run Wokwi CLI init, so we can jump straight into editing this diagram. Let's add 2 buttons for the inputs 4 and 5, and press D to duplicate it, 2 to set it to blue, 1 connects to 5, 1 connects to 4, and these are pulled up the inputs, so we will connect the other side of each button to ground. Press A to add an LED and flip it, set it to green, duplicate it with D, set it to blue, connect the top one to 18, the bottom one to 19, and let's ground both of them. So the first one goes ground, the second one goes ground. Save and simulate. And now the LEDs are blinking. That's probably expected. Let's test the buttons. That's weird. When I click off them, there are a ton of messages in the terminal. Let's take a look at the source code. This is the GPIO interrupt handler. We can see that for each generated interrupt, it queues an event. And then we have this GPIO task that pulls events from the queue and prints this message for every event. So for each interrupt, we expect to get a single message, but we get many. Let's try to figure it out. First of all, pause the simulation, and we can see that pins 5 and 4 are configured as inputs with pull-ups, 18 and 19 as outputs as we expect, so it's probably not a pin configuration issue. We are going to use another powerful debugging tool, the virtual logic analyzer. It's going to show us the signals that go on the wires, so pin 5, pin 4, and also the UARTX, and ground is optional, but let's get it connected as well. start a simulation, click on this button, and we can see that it collected a few samples, and then click the other button. And when we stop the simulation, it will ask us where to save this file with the recorded signals. Click Save. We can open the recording with the free software called Pulse View, and we can see the 3 channels that we recorded. This one is IO5, IO4, and the TX of the UART. And now I want to show you a cool feature of Pulse View. So there is this analyzers pane, and we can actually get it to decode the UART. So if we type UART, we add a UART analyzer, it automatically detected the TX channel, and we want to display it in ASCII. And if we zoom in, we can actually see the data that was transmitted, like GPIO5, inter value. And if we look at this, we can see that we had multiple messages. And if we zoom at the IO5, we can actually now see the reason why. The problem was that when we clicked on the button, the signal was bouncing here, and we can see that we also had it bounce when we released the button. This can explain why we had multiple interrupts on each click. Let's go back to the simulation, click on the buttons, disable the bouncing behavior, and test it again. Now when we click on the green button, we only get a single interrupt message, as expected. The virtual logic analyzer helped us spot the problem real quick. And if you are curious about the button bouncing behavior, check out the documentation. We have seen Wokwi running in the browser, in VS Code, and now I want to show you a third way of using Wokwi from the command line. We'll use the Wokwi CLI, the same one that we installed before, but first we need to generate a token. We'll click on the link, create a new token through the web UI, give it a name, EDC token, and we are using Windows, so we will copy this one and paste it into the command line. Now we can run the simulation and we see the output coming to the console. So what makes this useful? Testing automation. At a basic level, we can tell that CLI to wait for a specific string like CNT2. And this is all we need to do for a simple test case that we can now run on every commit. Yay, test passed. Now, let's see how to take testing to the next level using a feature called automation scenarios. Each scenario is a YAML file that breaks down the test into a series of steps. We'll start with this example from the documentation and adapt it for our project. Let's call it button scenario.yaml, paste the content, give it a name, test button press. My name is Uri, and now we should define the list of steps. So first of all, we got a good example here. We want to press the button, but we first want to make sure that this CNT0 is displayed before we press the button. So we will add a wait serial step to wait for CNT0. Let's run again the simulation in VS Code to go through the flow that we want to test. First, we need to find the ID of the green button. We can see it when we move the mouse over one of the pins, that's BTN1. And when we click on the pin, we expect to get this string here. Let's copy this and go back to the YAML file. And now we have enough information to complete the scenario. Let's paste here the string that we expect after pressing the button. And the example code we copied already presses the button, but for the good measures, let's also release it, unpress it. BTN1, that's the green button, and we will wait 100 milliseconds between pressing it and releasing it by setting the pressed control to 0. And that's it. The scenario is ready and we can run it. Wokwi CLI minus scenario button.scenario.yaml. Wait a few seconds for the simulation to complete, and it worked! Scenario completed successfully. We can also use Wokwi together with PyTest Embedded, the embedded testing framework from Espressif. And this project, like many other ESP examples, already comes with some test case that expects the text CNT and some number to appear in the output. If we wanted to run this test on a physical device, we could write PyTest with target ESP32C3, but that of course won't work because I don't have the board plugged into my PC right now. Instead, I could just run the same PyTest command with --embedded services IDF and Wokwi, And that's all we need to do in order to run the same test in Wokwi. This setup with PyTest makes it very simple to switch between testing on the physical device and testing in simulation in Wokwi. Alright, this is CI time! I'm going to show you how to set up Wokwi inside GitHub Actions. Let's start! I've already pushed our project to GitHub, so we need to set up the Wokwi token first. We go to Settings, Secrets, Actions, and we create a new repository secret. We call it Wokwi CLI token. And then for the secret itself, we can copy it from the same dashboard that we did with the Wokwi CLI. Here I still have this open. We can copy it, paste it here, and add secret. Now we will switch to VS Code, create the workflow file, GitHub workflow, and we'll call it build test.yaml. I'll ask Copilot for help because I'm too lazy to write it from scratch, so GitHub workflow that compiles ESP32 project on every commit and dispatch. The LLM is working its magic. Accept. Not too bad. Let's bump checkout to v4. And this step should be ESP32 CI action. And we'll call it build project. And to build it, we need to tell it the target, ESP32C3. And we don't need those. Instead, let's add a step to test with Wokwi. We are going to use the Wokwi CI action at version 1, and it requires a token. So let's give it the token that we put in the secret. That should be Wokwi CLI token. That's how we called it. And we also need to tell it which scenario file to use. So that's the button.scenario.yaml. Save, commit, CI, build and test in Wokwi. Push, and let's see if we got it right. Let's go back to GitHub, switch to the Actions tab. Oh well, it's compiling, so I'll be right back. Back with some good old Dinoti. Let's check up on GitHub. Great, it's green. Let's click and see the details. So we can see it took about 2 minutes to build a project with the ESP32. And then 6 more seconds to test it with Wokwi. And if we open this step, we can see that it first installed the Wokwi CLI, then it ran the Wokwi CLI similar to what we did in the VS Code terminal, and it ran the scenario, and scenario completed successfully. Now let's make this project even more interesting and add a second chip into the mix. First, we'll rename the existing diagram to diagram.esp32c3.json, and then we can use Wokwi CLI init again to create a second diagram. Yes, I'm fine, and this time we'll choose the ESP32c6, and we got a second diagram JSON. Let's rename this one into diagram.esp32c6. Close the terminal, and now we need to copy the buttons. We can also copy the LEDs from the old diagram, Ctrl-C, to the C6, the new one, Ctrl-V, and let's get the buttons connected. So the green one goes to pin number 5, and then the blue one will go to pin number 4, and we can leave the LEDs disconnected for this demo, so let's just connect the grounds, save, and go back to the build test YAML file. We'll configure test metrics. This will tell GitHub to run our test each time with a different value for the target. So once for ESP32C3 and once for ESP32C6. And also set fail fast to false, so all the tests keep running to completion even if some of them fail. And now we can use this target parameter from the metrics in our steps. So let's just use the matrix.target here. And also for the diagram file, we are going to use diagram.matrix.target.json. And that's it. We are good to go. Save, CI add ESP32C6, push, and back to GitHub. We can see that it's now running both jobs in parallel for the C3 and C6, so I guess it's time to take another sip of the Dinoti. 2 minutes later and all green. And this is how you can run many tests in parallel on multiple virtual boards. We call this Wokwi in the loop testing. And now for some real-world examples. Our friends at Espressif use Wokwi to test their ESP32 Arduino core on every single commit. They run the tests on all the supported ESP32 chips using PyTest Embedded and the Unity framework. This way, they can immediately catch any regressions when they make changes or when someone from the community sends a pull request. If you are curious, you can find the actual test code in the repo under Tests Validation. We can see that they have a similar setup to what we did with one diagram file per chip, as well as a scenario file that pushes a button. Another great example is this ESP32 Spooky Maze game. Spooky Maze was built by Raimi Kalek from the Espressif Rust team to showcase the capabilities of embedded Rust on ESP32. Here, he has a GitHub action that uses Wokwi CLI to take a screenshot automatically and save it to a PNG file. And if we go to the Actions tab, we can see there the screenshot from the simulated LCD display. Those screenshots are really useful for visual validation of your embedded user interface. And now I'm going to show you how we use Wokwi to test Wokwi. We have this ESP32 test binaries repo, and it contains many precompiled test binaries from the ESP IDF, like these UART or I2C drivers, crypto accelerators, PSRAM, Wi-Fi, etc. For each of those test apps, we have a test scenario file, and we are running all those tests on a daily basis. Let's take a look at the Actions tab and see the results. Most are green, but we can see that a few days ago we actually had a regression. If we look inside, we can see a matrix with all the chips and all the tests that we run, over 150 tests in total, and we can quickly spot the test that failed. In this case, some changes to the ESP Wi-Fi driver caused incompatibility with the simulation. Thanks to this automated setup, we were able to quickly spot the issue and fix it the next day. If you want to set up a Wokwi GitHub action for your own embedded project, you can simply copy this snippet from the documentation. You can also find more examples, some of them include automation scenarios, as well as a blog post showing how to use Wokwi together with Platform.io to set up CI. Alternatively, if you want a complete ready-made setup for ESP IDF with PyTest embedded, take a look at Espressif GitHub ESP test template. This template already includes CI configuration for Wokwi in the loop and even optional hardware in the loop testing in case that you need it. One question that I frequently get is, what happens if the sensor or display that I want to simulate does not yet exist in Wokwi? In that case, you can create it yourself using the Custom Chips API. To get started, go to Wokwi Online, select the Custom Chip option, then type a name like LM75A, a digital I2C temperature sensor. Then define the pinout, and finally write C code to implement the logic of the simulation model. I think we have had enough content for today, so I'm not going to cover the specifics of the Custom Chips API, but if you ever need it, there is extensive documentation, and there is also a very good video tutorial from Psychogenic Pat.
Hey, I'm going to show you how to implement a custom chip to include in digital simulations using Wokwi from A to Z. And I mean, we'll go through the datasheet.
Well, thanks, Pat. And of course, when you finish writing your custom chips, you can publish them on GitHub and then use them in Wokwi on VS Code and of course in Wokwi for CI. We have been building Wokwi for the past 5 years, but we are not done yet. Let's take a quick look at what's coming up next. First, we keep adding new chips like the ESP32 P4, and later this year we are also planning the C5 and the C61. We are also working on the Wokwi viewer that allows you to simulate a firmware binary directly from GitHub. Let's take, for example, this Zephyr project repo from Benjamin Kabe. It contains some precompiled binaries for several Zephyr project demos like this C3 sensor shell. We can simply copy the link to the firmware binary and paste it in the viewer. Same with the diagram. Load project. And voila, the simulation starts immediately in the browser. Let's change the temperature of the sensor to about 40 Celsius and now have some fun with the Zephyr shell, trying to read it back. Sensor get MPU 6050 at 68. Yep, it worked. You can copy the link from your web browser and share it with anyone and they will get the same immediate simulation experience. And if you are like our friends at Adafruit and need more complex Wokwi automations, we are currently working on a new Python client library, so you can use Python to write complex test scenarios. Well, that's been quite a journey. I've spent over 25 hours preparing, recording and editing this talk, so I hope you enjoyed and found it valuable. You can find me on the Wokwi or Tiny Tape Out Discord. Ciao, see you next time!